Hello viewers, in this video we will discuss the operation of astable multivibrator. Astable means not stable. So this circuit has two quasi-stable states. This multivibrator switches from one quasi-stable state to another quasi-stable state without an external trigger pulse. It is also called as free-running multivibrator as it does not require an external trigger pulse for transition between one quasi-stable state to another. It is also called by two other names, square wave generator and relaxation oscillator. Before going into the topic, let me introduce the most important keywords of the multivibrators. They are state, stable state and quasi-stable state. State is actually voltage levels. They are high level and low level. High level means plus VCC, which is 12 volt for transistorized electronic circuits, and low level is 0 volt. In either way, it can be called as logic 1 and logic 0 in terms of digital electronics. The second one is stable state. Multivibrator will stay in this state indefinitely until the trigger pulse is applied. The third one is quasi-stable state. This is actually temporary stable state or unstable state. The circuit will stay at this state for short time interval t. To understand the operation of multivibrators better, we will see the switching properties of the transistor. Now let us find what are the output voltage and output current when one transistor is at off state as well as an on state. First we'll see when a transistor is at off state. When the input voltage applied between base and emitter junction of the transistor is less than the cut-in voltage, which is 0.7 volt for silicon and 0.3 volt for germanium, then the transistor goes to off state, which means the collector and emitter terminals are open circuited. So no current will be flowing through the collector terminal. So IC equal to 0. The voltage across the collector to emitter terminal VCE equal to VCC. Since the collector and emitter terminals are open circuited, the entire power supply voltage will be appeared across the output terminal. Let me summarize this. When a transistor is at off state, the collector and emitter terminals are open circuited. The collector current is equal to 0. The collector to emitter voltage is equal to VCC. Next we'll see the output voltage and output current when a transistor is at on state. When the input voltage applied between base and emitter junction of the transistor is greater than the cut-in voltage, the transistor goes to on state, which means the collector and emitter terminals of the transistor are getting shorted. So more current will be flowing through the collector terminal, which is equal to IC saturation. The voltage across the collector to emitter terminal will be equal to 0 since the voltage across the short circuited terminal is 0. Let me summarize this. When a transistor is at on state, the collector and emitter terminals are short circuited. The collector current is equal to IC saturation. The collector to emitter voltage equal to 0, which is equal to VCE saturation practically. Now we'll see the working of astable multivibrator. This is the circuit diagram of astable multivibrator. Here we can see two transistors Q1 and Q2 are cross coupled. The collector of transistor 1 is coupled to the base of transistor 2 through the capacitor C1. And the collector of transistor 2 is coupled to the base of transistor 1 through the capacitor C2. So the astable multivibrator uses two AC couplings. The resistor R1 is used to bias the Q2. The resistor R2 biases the Q1. The RC1 and RC2 are the load resistors or collector resistors of transistor 1 and 2 respectively. Here we could see two common emitter amplifier stages whose components are identical. When the power supply is switched on, both the transistors Q1 and Q2 are trying to conduct. Although components present in both the stages are identical, one of the transistor will conduct more than the other due to the difference in the doping levels of the transistor 1 and 2. Now let us assume that transistor 1 is going to on state and transistor 2 is at off state for our discussion. When it is on, the collector and emitter terminals are getting shorted. So more current will be flowing through the collector terminal, which is equal to IC saturation. The voltage across the collector to emitter terminal is equal to VCE saturation. This is almost 0 and this is coupled to the base of the transistor 2, which keeps the transistor 2 remain in cutoff. When it is off, the collector and emitter terminals are getting open circuited. So no current will be flowing through the collector terminal, which is equal to 0. Voltage across the collector to emitter terminal is equal to VCC. This is the one quasi-stable state of the astable multivibrator, which is Q1 on and Q2 off. Now the capacitor C1 starts charging towards VCC through R1 C1 and on transistor Q1 with positive polarity in the right side of the capacitor and negative polarity in the left side of the capacitor. As capacitor C1 charges towards VCC, the voltage of the capacitor increases step by step from 0 to VCC as 0.1, 0.2, 0.3 up to VCC. When the capacitor voltage reaches the cut-in voltage of the transistor 2, the transistor 2 will be driven to on state because this cut-in voltage is sufficient to turn on the transistor. When it is on, the collector and emitter terminals are getting shorted. So more current will be flowing through the collector terminal, which is equal to IC saturation. The voltage across the collector to emitter terminal will be equal to VC saturation. This is almost 0, which is coupled to the base of the transistor 1. So this will bring the transistor 1 from on to off. This is the second quasi-stable state of the astable multivibrator, which is Q1 off and Q2 on. Now the capacitor C2 starts charging towards VCC through R2, C2 and on transistor Q2 with positive polarity in the left side of the capacitor and negative polarity in the right side of the capacitor. As the capacitor C2 charges towards VCC, the voltage of the capacitor increases step by step from 0 to VCC as 0.1, 0.2, 0.3 up to VCC. When the capacitor voltage reaches the cut-in voltage of the transistor 1, the transistor 1 will be driven to on state. Once it is on, the collector and emitter terminals are getting shorted. So more current will be flowing through the collector terminal, which is equal to IC saturation. The voltage across the collector to emitter terminal will be equal to VC saturation, which is coupled to the base of the transistor 2. This keeps the transistor 2 in off state. So the circuit is now switched to the first quasi-stable state, and this process will be repeated. Thus, the transition between the two states is automatic without an external trigger pulse. Hence, it is also called as free-running multivibrator. Here we can understand that the output of the astable multivibrator keeps switching between plus VCC, which is logic 1 level, and VCE sat, which is logic 0 level. The output stays at logic 1 level for the time period T1, and then it will be switched to logic 0 level and stays at this state for the time period T2. The total time period of the output waveform is T, which is T1 plus T2. As this multivibrator generates square wave form without the input signal, it is also called a square wave generator. Astable multivibrator comes under relaxation oscillator since it generates non-sinusoidal waveform without an input signal. We'll see how to draw the collector and base waveforms. The first graph refers to the collector waveform of transistor 1. The second graph refers to the collector waveform of transistor 2. The third graph and the fourth graphs are drawn for the base voltages of transistor 1 and 2 respectively. The graph is divided into 3 time slots for discussion. During the first time slot, I have assumed Q1 is at off state and Q2 is at on state. And during the second time slot, I have assumed the transistor 1 is at on state and transistor 2 is at off state. The third time slot is similar to the first time slot. When we want to draw the fourth time slot, it should be similar to the second time slot, and so on. Now we'll see how to draw the collector waveform of the transistor 1. To draw the collector waveform of the transistor 1, we should see the states of the transistor 1. During the first time slot, the transistor 1 is at off state. When the transistor 1 is at off state, the output voltage of the transistor 1 is VCC. So the collector of the transistor 1 stays at VCC. During the second time slot, the transistor 1 is at on state. When it is on, the output voltage is equal to VC saturation. So the output of the transistor 1 will be switched from VCC to VCE saturation. The third time slot is similar to the first time slot. Next we'll see how to draw the collector waveform of the transistor 2. For drawing this waveform, we should see the states of the transistor 2. During the first time slot, the transistor 2 is at on state. When it is on, the output voltage is equal to VC saturation. So the circuit stays at VC saturation. During the second time slot, the transistor 2 is at off state. When it is off, the output voltage is equal to VCC. So the circuit will be switched from VCE saturation to VCC. The third time slot waveform is similar to the first time slot waveform. Next we'll see how to draw the base voltage of the transistor 1. During the first time slot, the transistor 1 is at off state. When a transistor is at cutoff, the base voltage is less than or equal to cut-in voltage, which is initially at minus VCC. This curve shows the capacitor waveform. During the second time slot, the transistor 1 is at on state. When a transistor is at on state, the base voltage is equal to saturation voltage. So the line is drawn for the VBE1 saturation. The third slot is similar to the first slot. Next we'll see how to draw the base voltage of transistor 2. During the first time slot, the transistor 2 is at on state. When a transistor is at on state, the base voltage is equal to VBE saturation. So this line is drawn for the VBE2 saturation. And during the second time slot, the transistor 2 is at off state. When a transistor is at off state, the base voltage is less than or equal to cut-in voltage, which is initially at minus VCC. The third slot is similar to the first slot. Applications of astable multivibrators. As astable multivibrators are generating square waveform, they are used to produce clock signals for digital logic circuits. As astable multivibrators are functioning as oscillators, they are used to generate wide range of audio and radio frequencies. Astable multivibrators are used in digital voltmeter, switched power supplies, and in armature radio equipment to receive and transmit radio signals. They are also used in Morse code generators, timers, and systems that require square waveform, including television broadcasts and analog circuits. Thank you.